Hi, welcome to this intensive Julia workshop. My name is George and I will be walking you through it. The goal of this workshop is to take someone without basic familiarity with Julia and teach them everything necessary for them to use Julia like a pro. Hence the name Zero2Hero. The workshop is organized into 3 sessions. The first is about the core language syntax and the data structures. It also has caveats on how to write Julia code that is performant. The second session is about multiple dispatch, the core programming paradigm of the language, and how this allows you to write truly generic and truly extendable code. The last session simply overviews some Julia packages that play well with each other. So the videos you are about to see were recorded when I was doing this workshop live in the University of Göttingen in Germany. Check the video description below to find timestamps as well as links on where to download the workshop material. So keep in mind that I'm assuming that you have some basic familiarity with programming, and I also assume that you have Julia installed already. Check the website of the Julia language to find installation instructions. So without further ado, let's get started with this. And I apologize in advance because the questions of the audience are not really audible in the workshop. So I hope you have fun and this will be helpful to you. And please do the exercises.
So Julia is a new programming language. It was developed at MIT and it was released version 1.0 August 2018. The reason that we are doing this workshop, so to speak, is because this new language comes with a lot of promises about its capabilities and about its role in scientific computing. The important thing to note is Julia was developed with scientific computing in mind. So this was its target goal from the first commit, so to speak. And it is a language very similar to Python in some sense. It is interactive and it is dynamic and it is flexible and it has high-level syntax, but it also offers performance similar to the low-level languages like C or so. These are the bullet points that are summarized here. Now, in my perspective, there are other reasons to use Julia if you're a scientist, besides the obvious performance benefits. And these are what I summarize here. And of course, this is in my own personal opinion. And why I think you should try to do this, you should try to use Julia, is because it is a language that it's simply too fast, or the fastest one in my experience, to go from the conception of the problem to the solution of the problem. And these steps entail much more than just running code. So you care much more about how fast your code runs. What you care mostly about is how fast you can get your idea into runnable code. And the part that runs is actually a minor thing, in my experience. Another reason is how well Julia plays with itself and with other languages. What I will show in the second session is how easy it is to extend and use other people's software packages or modules without having problems. And I think this is very important in a world that really tries to go into open source software, open science, and all this kind of jazz. So now I will actually start immediately the first session. I have rehearsed these sessions and it takes me about an hour to go through the notebooks, which means I have reserved the remaining hour for your questions and so that you can solve the exercises. By the way, Ulrich told that you can just get credits. I will fight so that you don't get credits if you don't solve exercises. And I'm totally serious about this. Okay? So do your exercises. They are super easy, I promise. So we are starting. The Julia syntax is very straightforward. And we will start with reviewing this. Assignment in Julia is done with the equal sign, as you would expect. And you can assign anything to anything in some sense. So there is no special rules that you can assign only numbers. The variable names, maybe something to clarify. I am assuming basic programming familiarity in this workshop, okay? I will not teach you what programming means. I will just teach you Julia. I assume you are familiar with the basic concepts of programming. All right. So variables name can include pretty much any Unicode character. And strings in Julia are created with the double quotes, and the single quotes are exclusively for characters. And I mentioned Unicode, so most Julia editors, like the Jupyter Notebook over here, offer what is called LaTeX completion. So if you press slash and then a LaTeX command, and then you press delta, what Julia will do is transform this to the appropriate Unicode command, Unicode symbol. And very important, all Julia operations return a value. This is super duper important. How many of you are Python users? Please raise your hands. So in Python, once you do an operation, so you type x equals whatever operation, you don't see what x is. In Julia, you do see what x is, which I think is really, really important for efficiency. So the first basic assignment, I assigned the value 3 to the variable x, and I see 3. I can do basic math. For example, I raise y to the power 2.5. And here I demonstrate the Unicode power. So as I mentioned, if I type slash delta and then I press tab, I get the Unicode symbol for delta. And as I said, any Unicode symbol in Julia is completely valid. In fact, in the next line, I take it to the next step and I assign smiley faces to variables. I'm not claiming this would lead to readable code, but you could do this. Right? You could type, let's say, smile and then press tab and select the smiley face, and it would work. And you see, I can't do operations with these faces because indeed, if I use them as normal variables, it just works. Okay, so as I said, assignment returns value, prints the value by default, but you can silence this by using the semicolon. So if I type x equals 3 with semicolon, the result will not be shown to me. Okay. So as is with most languages, basic math operators have their equals version. So if I type x plus equals 3, this actually means x equals x plus 3. And the same story happens for subtraction, multiplication, etc. Something very nice that I like about Julia is that if you want to do number multiplication with a variable binding, you don't have to use the star sign as you would do in normal math. So if I want to type 5 times x, I don't have to use the star, which is multiplication, provided, of course, that I type the number as a literal. So I cannot type xx and this to mean x times x. But I can type 5x without the multiplication sign. So this is a completely valid expression. Okay, something that we will discuss much more in the second session of the tutorial is types. But for now, I just want to mention that every variable in Julia has its own type. What does this mean? Well, this simply means that numbers can be integers, they can be floating point numbers, they can be rational numbers, they can be irrational numbers. And this is represented in Julia by this type. And to understand or to learn the type of the thing, you use the function type of. I will go into detail in functions in a bit, but for now, this is important. So if I type type of parentheses and I put a variable inside this function, it will tell me what is the type of the thing. So the type of the cat face is an integer with actually 64 bits. And the type of 1.5 is a floating number, again with 64-bit precision. And the type of this string is actually string, as you would expect. Another thing about basic syntax that I find very convenient is that you can interpolate values into strings. What does this mean? Well, this means that I can use a variable inside of my string and get the value of the variable interpolated into the string. And this is done with a $sign. So for example, I have here a string that says the value of the cat face, and here I type the cat face. But then I add the cat face again with the $sign. And what this will do is we'll take the value of the cat face and put it into the string. So you see that once the string is computed, instead of the cat face, I have 1, which is the value of the cat face. And in fact, you can do this for any valid Julian expression with the $sign. It doesn't have to be just a variable. You can, in fact, do any numeric computation inside this interpolation syntax. For example, here I'm doing this math inside a string, but then the actual value, the resulting value of the math gets put into the string. So this is as far as basic syntax is concerned. Now we can see some basic collections. So, of course, collections are simply collections of elements, and you can index any collection with the bracket syntax, all right? So if you type some collection, and bracket, index, and then close the bracket, this will index into the collection. Important that I actually forgot to write here, but maybe I should do it right now. Julia indexing starts from 1. All right, Julia index starts from 1. So the first type of collection is the tuples. The tuples stand for an immutable ordered collection of elements. They are mostly used when you want a small collection and the elements of the collection are not of the same type. And the syntax to create such a tuple is the following. You open a parenthesis and you start adding items and you separate the items with a comma. For example, here I define a collection, a tuple, which is 2 strings and the number pi. And once I evaluate this, okay, I got the collection. So this is a tuple. And I can get the first element of the collection by typing the index 1. And it gives me the first element of the collection. So this is how it works. Now another collection, very similar to the tuple that we introduced here, are the named tuples. The named tuples are exactly like tuples, but you can specify things by name as well, but not only by order. So here in the first collection, I specified the elements by their order. The first element is purple, the second is cat, etc. In the named tuples, the same thing can happen. I can specify things by order, but I can also specify things by name. The syntax to do this is as follows. You again open a parenthesis and then you type the key 1 is equal to value 1 and the key 2 is equal to value 2. What does this mean? So if I create this named tuple with this syntax, here I created this named tuple and it has these 3 elements. The 3 elements it has, it's 5, string, and 1.6. These elements have a key that specifies them and the keys are X, Y, and Z. Now I can access these elements of this named tuple with normal indexing, so I can get the first element, which is 5, but I can also access the elements by name. And to do this by name, I can use either dot, so the object dot the name, or I can use parenthesis and symbol. We won't get into symbols, but I'm just telling you that this is an equivalent syntax. So you could still use the brackets if you wanted. So now I got the value of 5, but I didn't got it by its order, I got it by its name. All right. Did I zoom out? Okay. So dictionaries is the next step of collections, and they are unordered, mutable collections of pairs of key to value. So they are intended for sets of relational data where you have data of the same type. All right. So a dictionary typically contains stuff of the same type. And the syntax to make a dictionary is very similar. You open a dictionary by calling dict, and then you say, okay, I want the key 1 to map to value 1 by using equals and then the greater sign. So this is the syntax for a dictionary. So here I create a dictionary that represents, let's say, a phone book. And this phone book maps the name Jenny to the number whatever and the name Ghostbusters to the number whatever. And once again, similarly to before, I can index a dictionary with its key. So here I can only get variables by their key because the variables have no order in a dictionary. So I can type my phone book Jenny, but I cannot type my phone book bracket 1. This is not possible. Now I mentioned that dictionary is mutable thing. I will talk about mutability in more detail in a moment, but in principle, this means that I can simply add new entries to this dictionary without having to create a new one. And you do this very simply by using the syntax that you would use to get a new entry, but then actually using the assignment operator, the equal sign, and adding the new entry. So here I add a new entry to my phone book about Buzz Lightyear, and then I display the entire notebook, and you see that now the notebook has 3 entries. Okay? So I don't know if I made this clear, but if you will have questions, you are supposed to interrupt me, right? There is 30 minutes allocated for your interruption, so yes. Yes, they are. I will talk about this in a moment. You cannot add stuff there. Yeah.
So do all the elements have to be of the same type?
Yes, all the elements have to be of the same type.
What about the keys?
The keys also have to be of the same type. All right, now we go to arrays. Arrays are mutable ordered collections of the same type. They don't have keys. They just are a collection of the same type of items in order. They are mutable, and they are in general intended for large containers with many entries. Important, the element type, so what is the thing that my array contains, is completely independent with the dimensionality of the array. What does this mean? This means that a matrix and a vector of vectors are two completely different things. I stress this for the Python users because in Python this is not the case. So how do you create an array? You use brackets. You open a bracket and you add the item separated by comma, and then you close the bracket. So here I create an array. By the way, so I'm not confusing anyone, one-dimensional arrays, like the one I just made, are typically called vectors, okay? And two-dimensional are called matrices. I may use this name sometimes. So here I made an array that has some strings, okay? And here I make an array that has some numbers. And here I make an array that has both numbers and strings. But of course, I told you that arrays are supposed to have the same element type. So how did I do this? How did this work? Well, what I created here is in fact an unoptimized version of an array that can contain any element type. And in fact, you can see this here. This word after the array name actually tells you the elements that this array contains. And here you can see that it contains any, which means any type of element. Of course, having such a container is terrible for performance, but we will talk about this in a moment. But in general, it is true that you must have the same type of elements in your array. And this is true here as well. It just so happens that I chose to have any type of elements as my type of elements. So, of course, you can have arrays of arrays or vectors of vectors, which is what I do here. I open a bracket, and then I open a second bracket because my element of my outer vector is actually a vector in itself. So this is pretty much a vector of three vectors, okay? If you want to make a matrix, there is a different syntax, and you add the elements separated by space, and then you add a semicolon and you go to the next row. So this is like adding the elements of a matrix row by row. So it visually, when you write the matrix, visually it is the same as the matrix you are actually creating, okay? Like this. Another way to make matrices is to actually use functions that initialize a matrix for you. For example, I could call the function rand n, m, and what this function would do is it would create a matrix for me that has n times, that is of size n times n. So these are the two most common ways to create matrices in Julia. Now, if you have matrices, they have two dimensions. So in principle, you would want to be able to index both dimensions at the same time. And this is, of course, possible and with the same bracketing syntax. So if I have a two-dimensional array and I index it with two numbers, in fact, the first number is just the column that I go, and the other is the row, or the other way around. I mix the rows and columns, but you get the point. So now I mentioned that these matrices and these arrays are mutable collections. So this means that I can change their elements or add new elements or remove elements. So this is what I'm showing here. I create this Fibonacci vector that has these numbers, and then I say, okay, the first entry of this Fibonacci vector, I want to make it 15. And then I show the vector. Yes. And of course, as expected, the first entry changed to 15 instead of 1. If I want to add extra entries, I can use the push function. So here, the push function that ends in the exclamation mark does the following. It takes some container, and it adds this argument to this container. So here, what I'm doing is just adding the number 16 to the Fibonacci vector. So the functions push and pop are useful with arrays because they allow you to either add one element at the end or remove the last element. Last thing before we move into the next collection type is the colon symbol. So here I have a matrix of 3 by 3 size. Let's say that I want to get the first column of this matrix. How do I do this? Well, I index it normally, but in the column index, instead of adding a number, I add a column. This means get all the elements in this entry, so to speak. So in fact, if I type this, it will give me the first column because I got all the rows and I set the first column. Okay? Yeah? Yeah. Yeah. No, you just type zeros instead of run. Cool. Not really. Yeah, if you want to do it element by element, then yes, it only makes sense this way. But we should talk about this more during the break. There are optimized ways to do this efficiently. Yes. Yes, I will go there. Don't worry. I will go there. Can you wait a bit? You just type question mark and then the function name. Okay. All right. Okay. Last collection type are the ranges. Ranges are super duper useful things. They are simply shorthand notations that define a vector. And this is done with the following syntax. You have start, colon, step, colon, end, or you can use the actual function range that creates a range with the, I think, intuitive syntax. So what does this mean? This means that I have numbers that are starting from 0 and go up all the way to 5 with a step 0.01. And of course, ranges are not unique to numeric data. You can have ranges with anything that extends this interface. For example, here I have a range of letters that goes from A to Z. Now, ranges are printed in this short form, but if you want to see all the elements they contain, you use the collect function that simply takes the range and makes it an actual vector. So if I collect the letter range, I get all the letters, as one would expect. Why are ranges cool? Well, because they are not vectors. Ranges do not store all the elements in memory. They instead produce them on the fly. So if you have equally spaced data, you should use a range instead of a vector. It is in general preferred. Yes?
Where was the semicolon in the range function?
Sorry, it's the syntax is this one. Where is it? This is the syntax.
But in the next row, there's like
These are two alternative syntaxes that you... when I go into the functions, you will understand this a bit more. Okay, just be a bit more patient. Okay, any other range questions?
Is there like log space?
I will get to this in a moment as well. There is no log space, by the way. And I'm happy for this. So this is why ranges are cool. They don't store elements in memory, but ranges are also useful when indexing arrays, because you can, in fact, use a range of integers to index into an array. How does this work? Let's say I have a 4x4 matrix, and then I type the following syntax. I type range 1 to 3, and then 1. So this means simply the following. Take the first 3 rows, but take the first column. So in fact, this would give me these 3 numbers over here, which is exactly what it does. So this is a very useful application of ranges. And of course, I can use range in every dimension of the array, not only one of them. Okay. Cool. All right. I'm only mentioning this because we have Python users, and this is something that you do a lot in Python. So you can do list comprehension in Julia as well, which works almost in an identical way with Python. So you can make a vector that has a specific form of some expression for every element in some collection if some condition of this expression applies also. So for example, here I create a vector that has the elements a squared, for a being in the numbers 1 to 10, but only if a is actually even. And this gives me the vector, so to speak. All right. So now we're going to, this is all about data structures, at least for now. And now we go into iteration. So iteration in Julia is high level. This means that you can iterate among anything that can be iterated. And it also has very simple syntax. In addition, you can extend iteration. In fact, the next session's exercises will have you make an iterator. So how does iteration work? Well, the first thing is the for loops, and they iterate over a container and then execute a piece of code until this iteration goes through all the elements of the container. And the syntax is very simple. It says for the variable in this container or iterable, and then you have the loop body. And you will notice, and then you have the end function, and you will notice that all Julia code blocks end with the end keyword. So for example, here I have a for loop that iterates over the entries of 1 to 5, and then calls the function println, which just prints the thing that you give the function. So I see the numbers. Something that you will typically see instead of the in keyword is the mathematical symbol for in, this, which works just as well. In fact, I only use the mathematical symbol in my code. So, of course, this n, what this n thing is, depends on what I'm iterating over. For example, if I iterate over a dictionary, in fact, what I'm iterating over is pairs of key to value. So if I iterate over my phone book, which if you remember is the dictionary, I iterate over pairs. Because I iterate over pairs, Julia allows me to directly disentangle the two values of the pair into actual variables. So here I get immediately the key and the value. Notice that if I have written instead pair in my phone book, then I would have to type pair 1 to get the key or pair 2 to get the value, okay? But I could untangle them immediately. All right, next iteration protocol is the while loops, and they are very simple. They execute a piece of code until a condition is true. The condition is checked at the beginning of the while loop, and the code does not execute if the condition is true. No, sorry, false. The other way around, of course. So, how does this work? Well, it's very simple. I start with some number, let's say 0, and then I start to iterate over something until this number is greater than 5. When this condition becomes false, then the while loop will stop. Got it. Yeah, that's it. I think it's straightforward. I don't have something more to say here. Yeah. All right. Conditionals. Conditionals execute a specific code block depending on what is the outcome of a given Boolean operation. And notice that as with other languages, this and symbol and this vertical line are the Boolean and or operators. So the first conditional block is the if syntax that goes as follows. If some condition 1, then do this option 1. Else if some condition 2, then do this option 2. Else, if all else fails pretty much, then do the option 3, and then you see the end keyword again. So this evaluation is done sequentially. So you start with the very first check, and you continue all the way down. For example, here I have x and y to be 5 and 6. And then I say, okay, if x is greater than y, then give me x. Otherwise, give me y. Straightforward. Something I haven't said so far. By default, in Julia, all code blocks return the last evaluated expression. Okay? So here, this code block returns the value y because this is the last expression that it evaluated. Okay? This happens for every code block in Julia. It's not specific to if or while loops or whatever. Okay. Now, a nice short syntax that you can have for short if statements is the ternary operator. That goes like this. This is the syntax, and it says, check condition A. If A is true, give me B. Otherwise, give me C. And this equates to this simple if-else statement. And the if-else statement that I wrote here, this one, would be equivalent as a ternary operator like this. So of course, this goes without saying in some sense that both Boolean operators as well as conditional code blocks can be nested to arbitrary degree. So for example, this is a perfectly valid Julia expression that nests two ternary operators that becomes a bit clearer once you add a parenthesis. Because what it does is it checks one condition, and if it's true, it gives you a number, but if it's not true, then it does another ternary operation. It checks another condition, it gives you another. So this would translate into two nested if loops, for example, if you wanted to go with a verbose syntax. And of course, as with pretty much every programming language, Julia has the break and continue keywords that either completely skip an iteration or completely stop the iteration altogether. For example, I have this nice loop over here that iterates from numbers to 1 to 100. But if the number is odd, then I skip this iteration step. And if not, I print the number. But then if the number is greater than 10, I completely break the iteration. So you see that the number 12 is indeed printed because, in fact, this check happens after the print statement. This is why you see the number 12 here. Okay.
What is
Sorry. This is short circuit AND and short circuit OR operation. Do you know what this is? Okay, so the short circuit is something that comes from C, and it works like follows. Normal Boolean operators have to evaluate both sides to do the operation. Short circuit does not work like this because you know that if you want to say true and false, you know that false and true. You know that the outcome beforehand. You don't need to evaluate both aspects. I don't know. Does it make sense? Okay, perfect. Okay, now we go to functions. So functions are the bread and butter of Julia that heavily support functional programming. Functions are objects by themselves, and you can assign functions to any variable, for example, and you can really use them as any other value. So functions in Julia are declared with two different syntaxes. The first is the code block syntax that starts with a keyword function. Then you have the function name, and then you have a parenthesis, and you start listing the function arguments. Then you have the function code block, and then you have the end keyword. The other way to define functions is with the sort syntax, or the mathematics syntax, how I call it, where you start with a function name, you open a parenthesis, you list the function arguments, and then you add the equal sign, the assignment operation. And then you add the actual expression. So this literally assigns this expression to this function. They are both completely equivalent. There is absolutely no difference between the two, really no difference. So when you want to call a function, you have already seen how this works. You type the function name, and then you use the arguments you want to call the function with, which here is 5. Now, the cool thing, or at least in my eyes, the cool thing, I don't know if you agree, about Julia is that you can have both positional optional arguments as well as keyword optional arguments. What does this mean? Positional arguments are specified by their position only. Keyword arguments are specified by their keyword only. So here, I define a function that has both of these things. The function is called g. It takes the positional argument x, and then it takes the optional positional argument y. Then I add a semicolon, so I can start listing the keyword arguments. Who had the range question? You did? This is what the semicolon means. So z now is a keyword argument. I cannot specify z by position, but only by name. Perhaps some examples will make this a bit clearer. Here I call z with 5. 5 stands for x because x is the first positional argument. The other arguments get their default value because I didn't specify them. Now I call z with 2 positional arguments. These are x and y because these are the positional arguments of the function x. Z get its default value. Here I call z with the first positional, g with the first positional argument, and then the z keyword argument. Keyword arguments don't have order. There is no such thing as first keyword argument. Okay? And now I call z with all arguments it can take. And just a demonstration, here I'm trying to give 3 positional arguments, as if I could give z by position. This is not possible, and you see I get an error over here. Okay. Duck typing, I don't know how many are familiar with this. Yes? Yes?
When you
We will get to this on the second session. It's a bit advanced for now, okay? But be here in the second session.
The positional arguments are always coming first, or is there?
Yes, the positional arguments always precede the keyword arguments. All right. So Julia functions work with whatever input makes sense. So this means that there is no explicit declaration of your input unless you want to do this. What does this mean? So let me show the function g once more. The function g takes these three arguments and multiplies them, okay? These three arguments don't have to be numbers. Anything that supports the multiplication function will work with this function g. For example, if I give g the first argument to be a 3 by 3 matrix, then what g will do is simply multiply this 3 by 3 matrix with the other two remaining arguments, which happen to be numbers. I can also give this matrix to all three all three arguments of the g function, and what this function will do is actually a to the third, so matrix multiplication 3 times over. And I can also give strings to the g function because in Julia, the multiplication between strings is string concatenation. Yes?
So is it like mathematical matrix multiplication, or is it element-wise?
No, it's mathematical. Element-wise has an explicit different syntax in Julia. We'll get to this in a moment.
So you would get an error if either mentions.
Exactly, yes. You would get an error if here for Z you gave a, I don't know, 2 by 2 matrix. Yes. Okay, but of course, this is pretty much the same error that you see here, because now I'm trying to multiply number with string and this doesn't work. It gives me an error. Okay, so let's talk a bit about passing by reference now, and a bit more about mutating values. So mutable entries in Julia are passed by reference if possible. What does this mean? Well, you can imagine for a moment that you can separate the Julia entities or so into mutable and immutable. Mutable means that you can literally change something in the place it is in your memory, in your computer. Immutable means that you cannot do this. And if you give a mutable object to a function, this is passed by reference. This means that if I change this mutable object inside the function, the change is reflected in the object outside the function, okay? So let's see how this works. Here I create a vector that has 5, 5, and 5, and I change the first entry to 6. By the way, someone complained that Julia indexing starts for 1. This is massively more intuitive because you know that the number you index corresponds to the element's order. The index 1 is the first element. Index 2 is the second element. This is, in the long run, massively more intuitive. So tuples are immutable. So if I create a tuple and I try to change its first element, you get an error. So if I want to change the element of a tuple, the only way to do it is to create a new tuple from scratch, which is what I do in this command. So let's see how passing by reference works. Here I create a function called add3 exclamation mark that takes something x, and then it adds 3 to the first entry of x, and it gives me back x. So keep in mind I mentioned that all Julia code blocks return the last computed value. So here I could erase the return statement and nothing would change, okay? The return statement is mostly useful for code clarity and for if statements. So anyway, I create this function that adds 3. Then I create a vector that has 5, 5, 5, and I give this vector to this function. And then I see the vector. And sure enough, the first entry of the vector is different because it has been mutated in place in the function. By convention, functions in Julia that mutate their arguments end in this exclamation mark. This is not necessary from the language, but it's a convention that everybody uses. So, for example, to demonstrate this convention, let's see the difference between short and short exclamation. So I have here the vector 3, 5, 2. And then I sort the vector 3, 5, 2, and I get the vector 2, 3, 5. Then I look at the original vector v, and I see that v has not changed, because what I got here is a new vector. However, I can use the function sort exclamation mark to sort v in place. So now I get the same sorted vector, but in fact, I didn't create a new vector. You see that my original vector got sorted. I didn't get a new one. And now we go into the question of the help system. If you type question mark and then a name, Julia will give you the documentation string of this name. So here I type question mark and I give the name of the function type of, and Julia gives me the documentation strings. In general, this is really useful. The documentation strings tell you how you call the function and what the function does. So keep this in mind during the exercise session. Okay, broadcasting. So Julia compiles, yes?
So if it by default goes to passing the reference hub, do I control if I don't want that to happen?
You don't mutate the vector in the function.
So do I have to create a copy?
Yes. Sorry, now I get. Yes, you pass a copy. There is no other way to control this.
So in every function, I would first copy the vector and then work on the copy.
Of course. If the function mutates, the better way would be to have two functions, one with the exclamation mark and then one without the exclamation mark. This would probably be more convenient than adding copy in every function call. It's your choice, I don't know. So, yes.
How about to make a different version of the same function so that it figures out what it gets?
Yes, this is actually what we will do in the second session after lunch. So don't miss it. It's going to be awesome. Okay. Typically in Julia, you don't have to vectorize your code because the standard for loops are really fast. However, it is very often the case in scientific computing that you want to do operations element-wise. And the way you do this in Julia is with a very specific syntax, which is called broadcasting. Broadcasting is in general how you would call element-wise operations. So how does broadcasting works? Given any function or any operation, you can apply this function or operation across all arguments element-wise by adding a dot between the function name and the parentheses, like this. So let's return to this function g, but now define it without keyword arguments because broadcasting does not work on keyword arguments. So we have a vector 1, 2, 3, and what I want to do now is apply this function h element-wise across this vector x. The way to do this is to type h and then dot and then x, and you see that I get the element-wise answer. Of course, this broadcasting thingy really works across all arguments. So for example, if I want to do element-wise multiplication of 3 vectors in a row, which is what this function h does, I simply create these 3 elements and then I simply use the broadcasting syntax. And in fact, the same would work with matrices. For example, if the first element of this function, the first argument of this function is a matrix and the other 2 are vectors, you could still do element-wise multiplication. You would get each column of the matrix to be a vector, and you would element-wise multiply with the other vectors. And then you go to the second column, and you do the same. And this is, in fact, what happens if I have a matrix over here, this matrix, and then I have 2 other vectors, the one that goes from 1 to 3 and the one that goes from 0 to 2, and then I broadcast over this thing. Let me evaluate this. And once I broadcast this thing, Julia tries to understand what should be broadcasted, what should not be broadcasted, and what should the dimension of the output be. And broadcasting is how you make an exponential range. Who asked? You asked for an exponential. Someone asked. Yes, this is how you do it with broadcasting. And you get numbers that are exponentially going from minus 10 to the minus 3 to 10 to the 3. So, important. Notice that when you have infix operators, so plus or minus, which are not called like functions but are put in between the arguments, you put the dot of the broadcasting before the operator symbol, not after, because there are no parentheses here. Okay, is this clear? Is broadcasting clear? Broadcasting is super useful for writing concise code, so you should really try to understand it. If you have questions, you should really ask them. Yes?
So somewhere top we have the function h operate on a vector?
No, broadcasting does not pass by reference because broadcasting always creates a new output. So the result is always a new matrix. You cannot. There are ways to do broadcasting in place, of course, but I think I'm not. Am I showing this? So you could, if E existed, imagine that E exists, is a vector that has 7 entries. If I did this, it would be in place, an operation in place. So E would get an in place change of values. Okay, so this somehow answers your question, I think. Does it? Cool. Okay. So performance of Julia. So Julia matches the performance of C not because you have better compilers than Python, but because you have better design than Python. No, seriously. So Julia is interactive like Python, but this does not mean that it is an interpreted language. Julia is a compiled language. What does this mean? This means that when I type this command over here, this command gets first compiled and then I get the answer. Every function call in Julia gets compiled on the given input types. And of course, this compilation happens only once per set of given input types. And in fact, I have cheated you. I have pre-run this notebook before this tutorial started. So all my functions are compiled and I don't have to wait, let's say, half a second before I see the answer. But in general, be aware that when you run a function for the first time, it will get compiled and then you get your answer. So why do you have good performance? Well, it's simple, actually. When you have this compilation happening, you map the input types and all the operations and the types of all the operations all the way from the function start to the function end. Because this mapping is deterministic, the compiler can in fact do all the exact same optimizations that happen in C. Because if you think about it, this is how C compiles things. You declare all the types. And you do the same in Julia, but you don't have to actually declare them. Julia does it for you. So in a nutshell, this is how you get the performance of C. Very, very in a nutshell, okay? I'm not really a computer scientist. So, but what happens when this is not the case? When the types of your input arguments and all the function operations are not deterministically determined. That's such a sad thing to say, but anyway. What happens if this is not true? Well, then you have type instability. And in, let's say, 99% of the cases, when a new user of Julia has bad performance, this is the reason. So what does this mean? This means that if I write my function in a way that the types of the arguments change let's say, in a manner that should not happen during the function evaluation, then the compiler cannot deduce the output type of your function and cannot do the optimizations. Let me demonstrate this with a simple example. I define here 2 functions. By the way, is this visible for everyone? Okay, I'll try to zoom a bit. So these functions take no arguments, so I call them with no arguments, and they initialize a number, and then they do a small loop, and they divide this number with a random number, and then they return the number. And you will see the only difference these 2 functions have is how I initialize the number. Here I type 1, and here I type 1.0. What does this mean? Why is this important? Well, let's check the type of these things. Type of 1.0 is float. Type of 1 is float. Type of 1 divided by a random number is float. Sorry. Okay. The second was integer. Yes. Okay. So here I use a Julia package called benchmark tools. This is how you import modules in Julia. You use the word using, and then you use the word. What happened here? Okay, well, it's not a very good example, but I will try to demonstrate it. So what happens in this function is that inside the function, the variable x changes type. It goes from an integer to a float, okay? And this means that some optimizations might not be done. Now, unfortunately, this is not a good example because in the latest Julia version, type instabilities that have two small types are taken care of. So you see that the performance here is almost identical between the versions. But in general, if you have type unstable functions, you get massive performance slowdowns. And the slowdown increases both with the complexity of the types that you have an instability on, as well as with the amount of types that you have instability. Okay? So this does not really illustrate the problem, but it shows you how the problem actually works. It works because I used a different type for my X than the one I would get from its follow-up operations. Yes, I said this. So the other thing that results in type instability is the global scope. So in general, I'm not going to go into scoping rules that much, but in general, you can consider that Julia has two scopes. The global scope, which is what we use in this notebook, and the local scope. Local scopes exist within functions, for example, or within for loops, but local scopes don't exist in conditional statements like if. Now, by definition, everything in global scope is type unstable. This is so I can do this extremely useful thing. I can type x equals 5, and then I can type x equals 3, and it will work because x does not have a specific type because it's in global scope. And you cannot do this in C because you have to declare the type of the variable, so you couldn't change it, even if it was convenient for you. So, because everything in global scope can have any possible type, if you use a variable of a global scope inside an actually performant relevant code, you will get massive slowdowns because the compiler cannot know whether this X would be a string in the next second or it would be a matrix in the next second. It's not possible. So this I demonstrate in this loop. I create two random vectors of 1000 entries, and then I use this nice macro that times an operation for me. And what I do is I go through these two vectors, element by element. I square them and I add them to a number. But I do this in global scope. All three of these things, X, Y, and A, are in global scope. Then I do exactly the same thing, but in local scope, because I do these things inside a function. And you see, when I run this, so the operations are truly identical in every way, and I taken care to initialize A as a floating point number. But yeah, what you will see is that when we run this result, the global scope is much slower. And this is exactly because of the reason I mentioned. The compiler cannot know whether this A thingy would be a string in the next instance. And you can see this here. It's like, let's say, 300 times slower. So, conclusion so far. Put all performance critical parts of your code inside functions to ensure that your functions are type stable. Okay? There are tools to check for type stability, but we will discuss this probably in the exercise session. The second thing, what's the time, by the way? Oh, wow. Cool. So the second thing is allocation. What you really have to understand, especially if you are a Python user, is that when I type this thing over here, x equals, oh, that's too large. Let me make it. So when I type this thing, this creates a mutable entity. Creating a mutable entity costs. It costs stuff. You might be used to do this in Python, but it costs stuff. Like stuff, by stuff I mean time and memory. So you must understand that when you write this, when you write an expression that creates a vector or a matrix or whatever mutable thing, you pay two costs. The first cost is to actually calculate the numbers that go into this thing. So here it would be the cost of creating random numbers. The other cost is the cost of actually allocating a space in your memory to store this thing. And this is very important to understand because this will lead to more performant code. How? Well, how is very simple. Let's say that I want to do multiplication of matrices. There are two ways to do this. First, create the matrices and multiply them. That we would create a third matrix, that is their multiplication. The other way is to do in-place operations. These operations would do the same amount of actual number crunching, but they would not initialize a space in memory for the in-between products. How do we see this? Well, here I use the linear algebra module, so I can access this function over here. This function over here does in-place matrix multiplication. It takes three matrices, C, A, and B. It does the multiplication of A and B, but stores the result in place in a pre-existing C. So it does not create a new array. It only does the numeric computations. And then it sums this. Here, I do exactly the same thing, but I actually create a new matrix. So A times B is matrix multiplication, but this will give me a new matrix that I can use if I want, but I may not want it. So let's compare these two versions. Well, what happened here? Of course, I use different numbers. Okay, of course, the result will not be the same because I use different random numbers between the functions, but I use the same size of matrices. So the amount of operations is exactly the same, the amount of mathematical operations. But you see that the in-place is just a bit faster. Of course, once again, I say the same thing. In real-world scenarios where you have much larger matrices and much more matrices, this adds up. So in general, you should try to design your algorithms to create as little large new mutable entities as possible. And you should try to pre-allocate some containers and reuse them throughout your operations. And this is how you get better performance. Once again, you see that this is a small difference. In reality, it's a much larger difference because in reality, you have more stuff. Cool. I think we are on time. So you have like 1 hour to ask questions and solve the exercises. Try to solve at least 3 of them. They are super easy, I promise. All right, welcome back. So the second session is supposed to talk about the programming paradigm of Julia, which is multiple dispatch. If someone is completely uninterested in programming, this session may not be the best for you. But even if you have the slightest interest, I think this session will be great for you. In the first part, we mentioned that everything in Julia has a type, and Julia has a type system. What does this mean? This means that all these types are part of a connected hierarchy, and this connected hierarchy is where multiple dispatch is based on. So this connected hierarchy, you can think of this as a tree. So a tree is simply a graph that every node is a child of a previous node. There are not disconnected nodes. Every node is connected with the other in a hierarchical manner. This type system is dynamic in the sense that you don't have to explicitly declare everything from minute 1 to the end. So how do you find the types of the things and what types these things are connected with? The central node of this type tree is the type any, which means that anything any value is possible. And then you have subtypes of this type any. This is how Julia structures its types. For example, if you take the type float64 that we have already seen in the first session, and you use the function subtype. By the way, this is the compilation I mentioned. You see, I have not pre-run this notebook. We have seen the type float64, and if you use the function subtypes, you get all the subtypes of this type. Float64 does not have any subtypes because it is a leaf of this type tree. This means it is a node that has no children. It only has supertypes. It doesn't have subtypes. So if I type supertype, which is the function that gives me the supertype, it tells me the type that is the parent of this float64. Okay? Important, these functions, subtypes and supertype, they take a type as an input. They don't take a value. So for example, you cannot say subtypes of 5 because 5 is a value. It's not a type. Every value is associated with a type. Okay? I can continue scanning this hierarchy of types by asking what is the supertype of the abstract float type, and the supertype is real, the real numbers. Then I can ask which is the supertype of the real numbers, which is the type number, which includes complex numbers. And I can ask what is the supertype of the number type, which is any. So now we have reached the central node. This is a code block, so to speak, that prints the type hierarchy of the number. So if I go to the type tree and go to the number node, and then I want to see all the subtypes, this command does this for me. I'm not going to go into details, but this is nice for illustration purposes. So you see, you start with number, you divide to complex and real, you divide the reals to floating point numbers, to irrational numbers, to integer numbers, and to rational numbers. In this context, very useful is this operator called the subtype operator that simply tells you whether a type is a subtype of the other type. So here, because the float 64 is a subtype of number, you get true. But because float 64 is not a subtype of integer, you get false. Okay, so far? All right.
Are there for the complex numbers no different 64, 32 or so?
There are. We will get to this.
Why are they not shown in this table?
You have to be a bit patient, all right? So the types can be abstract or concrete. Concrete types is anything that can actually exist. Abstract types cannot actually exist in the sense that they cannot be instantiated. You cannot have a value that is of type real. It is not possible. So, and if you think about this as a network, concrete types are the leaves of the tree, of the network tree. You will understand this more as we go through the exercises. You will see what I mean with concrete types that can be instantiated and abstract types once we go into examples. So to go into examples, how do we make our own types? You can think of types as the Python classes, but you will see they are actually not the same thing. But think of them as a way to structure your data in your own custom containers, all right? So you define types using the keyword struct, and then you give the type name, and then you start stating the fields this type will have. Fields are simply the things this type will contain. Some types contain things, some types do not contain things. For example, the float 64 type does not have any fields. The type by itself is the value. Not the value, but you will see in a moment. You will see in a moment, I promise. So this way you create a struct, and this way you create a mutable struct. So if I create this B type, I could change its values in place, similarly with the way we discussed in the first session. So after I define these types, I can instantiate them, which means actually create a value that is of this type. And the way I do this is by using the default constructor, which calls the type name as if it was a function. So here I define this type A, and I call this type A as if it is a function, and I give it the two fields it's supposed to have, all right? And I do the same with the type B. So here, A and B are values, all right? They are variables that have a specific value. The value is of type A or of type B. Similarly, how the value 5.0 is of type float 64. All right? And as I said, the difference with the two is one of the two is mutable. The parent of A and B is any, because I didn't define any parent, so it's by default the central node. Yes, X and Y could be absolutely anything here. And we will see in a moment why this is a terrible thing to do. But for now, they are anything. So, thanks. How do you get the values of X and Y, the values that are actually contained in this type structure? So here you see that I have these two values, or these two fields that are X and Y, and they can store any value, as you just said. How do I get this value, though? Well, I get this value almost identically with the Python syntax. So I type the type instance A, and then I type dot and the field name, here x. So this would give me the x field of A, and this would give me the x field of B, all right? And because B is mutable, I can actually mutate this field in place. But for A, I cannot do this because A is immutable, okay? You see, I have here the error. Okay, so here is the point. As it was just mentioned, the way I defined A, this x and this y could be anything. This means, in accordance to the first part of the workshop, if I try to use this A in any function, this function cannot possibly know what optimizations to do, because it cannot know what data A would contain, in a sense. So, how do you take care of this? You take care of this by declaring types. So here, I define a different type called A good, where the fields have a specific type. Once again, you have to make the distinction. The value can be anything. The type of the value must be specific. So any float number is okay, but it has to be a float number, okay? And of course, by default, Julia will try to convert the given types to the types they have to be. So here I give integers as numbers, but Julia knows that this thing doesn't take integers, so it tries to do a conversion. And conversion may or may not be possible, no promises here. So this means that A is concretely typed. Concretely means that every every field of A is a concrete type, right? A type that can be instantiated. I could type here real. This is possible to do, but this is not a concrete type. Real is an abstract type. So now let's talk about abstract types, because they are actually useful. And the way they are useful is because they establish a hierarchy in the type tree. And this hierarchy is then used in multiple dispatch. So you define abstract types by using the keyword abstract, type, and then the type name, and then end. This defines an abstract type. Now, the way I did this C is a subtype of any, because I didn't establish any subtyping relationships. And of course, because C is abstract, it's not possible for me to instantiate it, to actually give it a value. So if I try to call this C with a number like I did with capital A and capital B, it just doesn't work. To make C useful, we use it in the type hierarchy. And we use this same subtyping operator that you see here to establish a hierarchical relationship between a new type that I define, D, and this type C. So now D is a subtype of C. And if I call the subtypes function for C, it will show me the type D. And as I said, this is not a type stable definition, because a number can be integer, can be rational, can be anything. So number is a concrete type, and if I declare a field like this, it is not type stable. But of course, you don't want to limit your structures to only store a specific kind of number, and you want them to be flexible and use floats and integers and all these things. The way you do this is with parametric types. This means that your structure, your type that you define, is parameterized with respect to other types. For example, here I define a new type called alpha, and with the curly brackets, I start the type parameterization syntax. So these curly brackets simply tell me that this type A is parameterized on this type capital T. And then A has two fields that are of the same type, and this type is T. Now here T is anything. It can be any type, string, float, whatever. But the important thing is that once I instantiate A, it will be concretely typed. Because, let me show you how this looks. I of course have to run this first. Because when the compiler sees this thing over here, it knows that this is the type alpha, but it is not just alpha. It is alpha with specification floating point numbers. So it is possible to optimize code and make it performant. And here, of course, I specified explicitly that it should be float 64, but I could instead let the Julia interpreter make this decision for me and understand that, okay, if I try to instantiate alpha with an integer and an integer, I'm probably trying to instantiate an alpha with parameterization integer numbers. So this is how it happens. However, if I try to instantiate alpha with a string and a number, the language will complain because it will tell you, I cannot do this, pretty much. Yes, and this doesn't work because strings cannot be converted to numbers in Julia. And of course, the number one and the string one are not the same because only the devil would want to put this in a programming language. But apparently, some languages actually do this. Yeah. Yeah.
So these parametric types, or the specification has to be a concrete type, right?
No. The example comes in a bit. The specification does not have to be a concrete type. But I know what you mean. If you want performance, it has to be a concrete type. But you can also make it an abstract type with a subtyping. I have it in a moment. You will see. So if you want the two different fields of your type to have different types themselves, you can simply parameterize your type with more types. For example, here I instantiate this, or I define this type that parameterizes itself on both its first field, but also on its second field. Now, to answer your question, at least briefly, I could type here this thing, and this would simply hint to the compiler that f could be any concrete type, but still a subtype of the reals, though. I could also type, no, this I couldn't type. I hope this is enough for now. So for this thing, I can make this have two different parameters, two different kind of values, a string and a float number. And you see this here. And you can see in the parameterization that indeed there are two different types that parameterize this thing. Now here is a bit more convoluted example, but this is an example you would see in reality. Because in reality, you don't want your types in general to be of any type, but it makes sense to hint what possible types could exist. Not for the compiler. The compiler doesn't really have a benefit from this. The human has a benefit from this. So here, if I try to instantiate this structure, I know that the first thing has to be some real number, this thing. The other field, the second field, has to be either a string or a real number, because here I use the union specification. Union specification simply tells me that, okay, it can be either of the two things. That's it. But it's still in a sense concrete because I want it to be a subtype of this thing. So f can be a string and it can be a real or a float. And the last field has to be explicitly an integer. I cannot change this. All right. Now, have you understood this part? Because it's really important for the following section. Are there any questions? Yes. Mm-hmm. So yes. Be careful. You cannot do this. This is different. This is the type. But if I type this is the value. You can get the field from the value, not from the type. If you want to see all the possible fields a type has, you use the function field names alpha. And it gives you the fields it can have. But this is different from the value. Yes, you type. So let me just make it easier for you. You just type the first field or the second field, or whichever field you want. You do it by name. So this is quite similar to Python syntax in a sense. So let me change. Yes?
I think what you should mention is that if you have an immutable struct like this one, and A or B is an array, then you can change the entries of the array even though the struct is immutable.
Yes.
And I found that confusing.
Okay, that's a good point. Maybe I should say it now. Mutability is defined with respect to the lowest possible level. This means if you have a tuple, which we said is immutable, right? And the tuple, the elements of the tuple are vectors. Vectors are mutable. You cannot mutate the tuple itself in the sense that you cannot add an additional vector to the tuple. But you can mutate the elements of the tuple because the elements of the tuple are mutable. So if I get the first vector of this tuple, I can add one more element to this tuple. Okay? Is this clear? For whom is it not clear? Can you raise your hand if it's not clear for you? All right. Okay. Cool. All right. So now we go into the multiple dispatch, which I think this is really some completely mind-blowing stuff here. So, and in the third session of this workshop, you will see multiple dispatch in action. Of course, here we will have toy examples, but in the third session, you will see how it is used in real Julia packages. What is multiple dispatch? Let's make first two definitions. Function, for our purposes here today, means the name of a function or process we are referring to, okay? Method means what actually happens when we use this name in a specific context with a specific combination of arguments. Let's make this clarification for now. So, what is dispatch? Well, first of all, you have the no dispatch situation, which is, for example, what happens in C. There, the function name and the method is the same. There is no dispatch, there is nothing to be decided. They are just the same thing. There is no change to be made. Let's see single dispatch. In single dispatch, it is possible to have different functional behaviors for the same function name. For example, if you think about Python, that uses single dispatch, it is possible to type array.setSize or axis.setSize, where here array could be an instance from NumPy and axis could be from matplotlib. This is single dispatch because in reality, what happens is that array is in fact the first argument of this function setSize. It is just kind of hidden from the user with this kind of syntax, but this is the reality. Array is the first argument of setSize, and setSize dispatches, so it decides its behavior from this first argument, which is array or axis or I don't know, whatever. Something extremely important, and it will be clear later on why it's important. Here, the method is the property of the type. They are not independent. The method setSize is the method setSize is a property of the array type or the array class in Python. Okay. And now we come to multiple dispatch, which is what Julia uses. In multiple dispatch, the behavior of the function, the method of the function, is decided based on the combination of every input argument. For example, I can define a method where the first argument is an array. I can define a method where the first argument is an axis. I can define a method where the second argument is an array. I can define a method where the first argument is an array and the second argument is explicitly a vector, and so on and so forth. What this means is that as a user, you get exponentially more expressive power in the sense that you can configure your system to take advantage of all your arguments. So if your first argument has 5 possible types and the second has 5 possible types, your expressive power is 25. While in Python, it would be 5 because you only get it from the first argument. All right. So how does this work? Imagine you live in a world that only 5 types exist, okay? If you have multiple dispatch, your function name can have 25 possible methods, let's say, if it takes 2 arguments only, because you have 5 possible combinations from the first argument, 5 possible combinations from the second argument. And in fact, if you add the third argument, you would have 125 possible combinations. In Python, you can only have 5 combinations, period, because you can only dispatch on the first argument. All right. So multiple dispatch works by following, in my opinion, easy to understand rules, but I have been using Julia for some years now. Let's see what you think. Based on this type hierarchy that we mentioned, this nice tree that the central node is any. How it works? When you call a function, Julia will try to find the method of this function that is most specific across all of its arguments. This means that if a method is defined for both the abstract type combination as well as the concrete type combination, then Julia will always call the concrete version of the method. This also applies to parametric types. For example, a vector with parameterization float64 is in fact a more specialized version of the simple vector with no parameterization. And this rule also applies to unions because, for example, float64 is more specialized than union of float64 along with string. So this is how Julia decides the method. Two important things before we go into the examples. Methods do not belong to the types. They are independent entities. And new methods can be defined after the types have been defined. You will see why this is important once the examples are in place. So what I will do now is create a simple example that uses some kind of animals and does some things with them. So the way to do this is to define an abstract type that I will call here animal. And then I define two concrete types that are subtypes of this animal. I create a dog type and a cat type. And you see that these types only have one field that is a name. And this name is a string. All right? So I define these, let's say, types, and then I instantiate them. So here, these four things are variables. Well, Fido is a variable of type dog, okay? Spot is a variable of type cat. Okay, these types are nice, but how do we actually use them in practice? Well, you use them in practice by using multiple dispatch. How do you do multiple dispatch? You define a method of your function using the type assertion operator in some sense. Here I create the function encounter. And I add a method for this function using these type combinations. My first input type would be any subtype of animal. My second input type would be any subtype of animal. This function then calls another function called meet, and it gets something from this function. And then it uses this second function inside some string. So this string, as you can see, it interpolates the names of the first and the second animal. Remember, $ is string interpolation. I then define this function meet, and I create a method for this function that dispatches on two input types, both of which must be subtypes of animal. So once I run this function with two combinations of animals, the behavior I just defined happens. Both the animals meet each other and pass by because this is what the function meet does. But this is the abstract level, and I can do something more specific. For example, what I do here is I add 4 new methods to the function meet. I add a method that I have the first argument a dog and the second argument again a dog, all the way down until I have the second argument a cat, and the first and the second argument both to be a cat. And what you will notice is that Julia says, okay, this is a function meet, and it's a generic function with 5 methods. If you observe this above, the first time I defined this function, it only had 1 method, this one. But now it has 5, because it has these 4. Now what will happen is when I call this encounter function, a more specialized version of the functions will be called because it exists. A more specialized version now exists. So now you see that if a dog and a dog meet each other, they sniff. Otherwise, they chase. Otherwise, they sling. Otherwise, I don't really know what they do. So this is how it works. And in all honesty, the real application of these systems in real complicated Julia packages is not much more complicated than this. You have the type parameterization, but there is nothing more to multiple dispatch. This is the way it works. Now let's see why this system is actually great. Because it is so simple to extend it. Let's say that we have designed this nice algorithm and we use this algorithm in our nice project, and somehow someone tells us, you know what, a third animal exists in this world, and it's a rabbit. Can we include this rabbit into our system? It is actually very straightforward. You define a type that is representing this rabbit. And of course, you make it subtype of the same abstract type. And then what you do is you just add two more methods to your meet function. So here I add a method that takes the dog and the rabbit, and a method that takes the rabbit and the cat. Okay, and finally I create a rabbit called hops. So now when I call the function encounter, I know that there are specialized methods that take the rabbit. For example, a dog and a rabbit and a cat, I know that they will wiggle or hide. I don't know what they do. But then I call the function encounter with a method that I have not defined a specialized version for. And what we'll do, it will actually just call the abstract method. Remember, we have defined an abstract method for any animal, and this method just gives the string passes by. And of course, I can call this method with new types as well. This is important to understand because the type rabbit did not exist when I created this abstract method, which is over here. The type rabbit did not exist when I created this, but of course it can still dispatch on this type. All right.
Does the type animal has to exist when you
define a method? Yes. You can only define methods for types that exist. Yes. Okay. You can inspect dispatch in some way, multiple dispatch I mean. First of all, the function methods is a function that takes as an input another function, and it lists for you the methods of this function. Okay, yeah. Another thing you can do is you can use this which thing here. So I'm not going to go into detail what this means, but if you use this syntax, which with an at in front, and then you simply call a standard function call, this which will tell you which method is actually called when you call this function, which is the method that has cat and dog and is defined at this cell block 41 at line 3. So now something that when I first understood it completely blew my mind. In Julia, all generic functions are fully and truly equivalent as far as how the language handles them. There is absolutely no benefit, let's say, to the plus function with respect to the encounter function that I just defined. It is simply another Julia function that has some methods defined to it. Of course, the plus function has much more methods. It has here 166 methods. But in principle, the way I defined my encounter function is really no different than the way Julia would define the plus function, or any function for this matter. So, the other thing you can do with multiple dispatch is because any function is equivalent with each other with respect to handling, you can just add a dispatch method to any function. So what I do here is I use the function plus from base. Base is the part of Julia that defines the basic commands. And I say that, okay, if I add two animals, I want the plus function to say their names and to say that they are animals. But if I add two cats, I want the function to say that cats are very cute. So how does this work? Well, I did this extension here. I evaluated the code block, and then I simply add the two animals I have created. And of course, the function plus did something else than what plus normally does. But if I add two cats together, you see that I get the different version, which is a more specialized version. All right? So here I have something we don't care about. And now we go into dispatch for parametric types. I have already mentioned this, but now you actually see this in practice. If you recall, we have defined this nice type here, alpha, that is parameterized on the type capital T. I can define methods for this alpha type based on either the really generic version without any parameterization, which is the first line. I can define a method with a bit more specialized parameterization, but still generic enough. And I can define a method that has exact parameterization, in the sense I want exactly this version of this type. So all three of these function definitions are valid for dispatch reasons, I mean. And then I use them in practice over here. So here it just tells me that it is a generic function because I used alpha with strings. Here it tells me that it is alpha with any number because I used it with any number but not float 64. And here I use it with float 64, and you will see that the more specialized version is called. And to really read more, you can go to the official whatever documentation. Questions so far?
Question. How do I make it statically timed?
Sorry?
How can I make my functions statically timed?
You have to explain to me what this means.
I mean, I want to throw an error if it's not a float, for instance, or it's not an int.
Yes. So here you would just type error instead of something. The answer is you do not define methods for abstract types. That's it. Although I would not recommend it. It's in general useful. But this is the answer, honestly. You just don't define methods for it. All right. So now let's see what time is it? Oh, all right. Let's see an example of how one would use this system to write truly generic algorithms. Generic algorithms are algorithms that you can really easily use and extend. Let's say that we want to create a simple linear algebra algorithm that takes a matrix A and takes a vector of vectors, okay, or any container of vectors. And what this algorithm does is this operation, the dot product between a vector, a matrix, and another vector. Okay, it just does this operation and accumulates the sum somewhere. This is a simple function for demonstration purposes, of course, that is defined like this. Here I use the linear algebra module so I can access the dot product function. So I define my function called inner sum. It takes the matrix and the vector of vectors. It initializes a counter, and in this counter, it adds the following product. Inner is a function that I define like this. It just gives me the dot product of some vector v with the matrix A multiplied with another vector v. It really does this operation that I saw here. All right? So this is a straightforward algorithm, has some, let's say, some imaginary use, and you can call it with a 3x3 random matrix and a container of vectors of size 3. Okay? And you call this function, and the function does its operation. Okay, that is great. What is important is that this code is generic in the sense that any input types that support this operation and the dot operation would work with this code. This is the duck typing that we discussed about in the first session. So this is generic. It works with whatever input makes sense. Of course, this means that if I use standard arbitrary Julia arrays, Julia will use BLAS. It's a linear algebra library. If I use static arrays, a different type of array that I haven't mentioned, then Julia will do something different. It will use unrolled efficient operations. Without me changing my algorithm, I just changed my type, or my input type to be more precise. But let's take this a step further. So in fields that use linear algebra a lot, like machine learning, people define this type of vector called a one-hot vector. This vector represents a vector that has zeros everywhere except one entry that it has 1 there. And I want to use this vector and use this vector in my algorithm. How does this work? Well, the first thing I have to do is I define this abstract entity called, not abstract entity, the type of this vector that is called one-hot vector, which I do here. This vector is very nice because even though it can represent a vector of 1 million length, it only needs 2 numbers to store it. Its actual length and where is the non-zero element. These are 2 integer numbers. Instead of storing 1 million integer numbers, you store 2. This is why this is useful. So I create this here. This is the one-hot vector that has a length and a specific length, and it has the index of where the non-zero element is. What you will see here is that I subtyped this vector from the Julia abstract vector. So the subtyping relationship says that this should be a vector, simply because of this. or for this thing to truly be a vector, I have to extend some methods that vectors should implement. Another way to phrase what I just said, one moment, is what I want to do now is extend the vector interface, all right? What is an interface? It is the type and a set of functions this type should be able to extend, to implement. Yes?
How do I know this set of functions? Where do I get this information?
You go to the documentation, or you experiment, but I don't recommend it. You just go to the documentation. That's it. Yes?
So what's the meaning of the bool and calibration?
Oh, this is that the values of this vector are Boolean. Because in the sense, what I said, the vector has either zeros or ones, and you can also represent this with Boolean, true or false. So how I know the interface, and the way you can do this is either by reading the documentation or by trial and error. You can take your pick. I don't know which one is faster, honestly, because here the interface is just two methods. That's why I don't know. So to actually make my vector a true vector, I have to extend two methods. First is the size method. Okay, I extend the function size from base Julia, and I say, okay, the size of this one hot vector is actually just a tuple that has its length. That's it. The other thing I have to extend is the getIndex method. The getIndex method is what happens when I do v5. When I do v5, in reality, what Julia does, it calls this function called getIndex, with the first argument my vector and the second argument my index. And the way I extend this function is I say, okay, is this index my non-zero index? If yes, then give true, which is actually 1. If not, give false, which is actually 0. So of course, I have to evaluate the size. Okay, so now I can instantiate this Julia type. And you see, I didn't even define displaying operations for this type. Julia automatically understood that this type is a vector and it knows how it should display vectors. And this is what it did over here. I did not do this. Julia did this. The only thing I did is I said, you know what? This is a vector. All right. So now let's see. Since this is a vector, would it work with our linear algebra algorithm? I'm going back so that you can see the definition of the algorithm one more time. This is the linear algebra algorithm, all right? It uses the function dot, the dot product function, and the multiplication between matrix and vector. Now, because this one hot vector is indeed a vector, this algorithm, you will see, it will just work. I didn't have to do any modification to my algorithm whatsoever, even though I created a struct from scratch. But now comes the important part. This algorithm worked, but the way it worked, it used a very inefficient algorithm where every element of the vector is multiplied with every element of the matrix. But this is not the reason I make this one hot vector. The reason I make this vector because I know that matrix multiplication can be super efficient. So if I think about this, what is this operation supposed to do if W and V are one hot vector? Well, A times V should in fact just give me the V column of A. So let's say the one hot vector has a non-zero element at the third row. If I do A times V, this will just give me the third, no, it will give me the third row, not column, but anyway. And then I do another dot product with another one hot vector that I know it has only one in a specific location. Then I know that this, in fact, will just give me the specific, how is it called? The element on this specific row of the result I have. So if you take some time to think about it, which you don't have to do now, you can just trust me. What in fact this operation should do is just this. It should just index my matrix at these locations in memory. This is what the operation should do. All right? You don't have to understand why this happens at the moment. But let's see why this is important, because we can use this information. We can use this information to change our algorithm without much effort. I will first, this is what I will do here. What I do now is I benchmark my linear algebra code with this one hot vector without doing any change whatsoever. I use this vector as a standard Julia vector. And then I do just one thing. I define a new method for the inner function that takes as a first argument a one hot vector and as a third argument a one hot vector. And it just indexes the second argument to the locations of the one hot vectors have their ones. I define this method, and then I benchmark the inner sum function again, this linear algebra algorithm. And what you see is that my performance went from 20 milliseconds to 57 nanoseconds. Now, the cool thing is not this performance. You could guess this performance by writing a dedicated algorithm from scratch. The cool thing is how little I had to change my algorithm for this to happen. This is the important part. The only change I had to make to my algorithm is, in fact, this line. I didn't change anything else about my algorithm. All right. How much time do we have left? Okay, I can say this. To really understand the value of what I just said, the value of how little things I changed, to really understand this, what I will do now in the following is compare how I would do this process in Julia and how I would do this process in Python. And you will see the differences on how easy or not easy this thing is. So let's say that there exists a type called RGB. And this type simply represents a color. It takes three values, red, green, and blue, and represents a color. And this type exists in both Julia and Python, okay? Someone now wants to use this type to make, for example, a color vector space or whatever they want. They somehow want to extend this type for whatever reason. How do you do this in Julia? Well, you simply use this type and you define methods for this type, just like I showed before. There is no difference. No difference. So here I use this Julia package. Okay, this is a bit incorrect here over here, but forget about it. And I just define methods that dispatch on this type, RGB, okay? So what I did here is I added a module on the top and an end in the bottom. I'm not going to go into namespaces because this is mostly for package development, but the way what this says is that here I start a new namespace that is called extensions to RGB. And I do stuff inside this namespace. This is what this says. Okay? That's it. Of course, I can extend existing functions with this type, but I can also define new functions with respect to this type. So here I define a dot product in color space that takes two arguments, that both arguments are this color type. All right? Sounds straightforward so far? How do you do exactly the same thing in Python? So the difficulty in Python is that the methods of a class are defined textually inside the class definition. You literally have to type the text of the method inside the class definition. This means you cannot add anything to this method once the method has existed. Once you have written once the class has existed. Once a class of Python is written down, that's it. You cannot add anything to this class. So if you really want to add a new method, you can either edit the original class, like literally editing the text file, or you can inherit from the original class. But both of these approaches have problems. If you modify the original class, you first have to convince the author of the class that your method is worth having in their software. And then if everyone convinces the author that their method is worth having, you have a single text file that is 5,000 lines of code for one class definition. And this is, of course, an unreadable mess. But the bigger problem is that the guy that wrote this class in the first place then has to maintain everyone else's class methods, which is also not optimal. The most important thing, though, is that you cannot change your mind without breaking people's code. If you added a new method for your class in Python, and later on you say, you know what, I don't like this method, I will remove it. This breaks everyone's code that uses your class, even if potentially that was not your intention. This is simply because everything comes from the same namespace. I won't go into details for that. We can discuss it on the break if you want more details. The second option is to inherit stuff. Well, this is great because it doesn't break anything, but it's not great for being usable because you cannot inherit the name. You cannot inherit RGB. You can inherit RGB, but you don't have RGB. You have another name called myRGB. So you create this myRGB and you make some extensions to this myRGB. The problem is that your extensions don't apply to the original RGB class. So no one can benefit from what you have done unless they use your myRGB, which is fair. But then a third person comes along and says, you guys, you know what? I want some different extensions. This person makes a your RGB. And then a fourth person comes along and says, oh, your RGB and my RGB are cool, but I want to make a method for both of them. Now I have to inherit both of them. And then there is our RGB. So I don't think this is very optimal. And the reason Julia does better here is for two things. First, you can define methods for a specific type after the type has been created. And you can define new methods, and you can define new operations for types that already exist. And in addition, because of the namespace separation, if you recall, when I wrote the Julia code about the extensions to RGB, I added here this module blah, blah. What happens is that in Julia then, the moment you type this command in your code, using RGB extensions, I don't know how I wrote it, something, okay. The moment you type this command, you have access to all the extensions I have done to this RGB class without using a different class. This is the important thing. If you use this RGB object in your code for whatever reason, simply by doing this line of Julia code, you get access to everything I have done in my extensions. But in case you are afraid, because I'm crazy and I will break everything, by not including this command, you don't have access. And the original definition of RGB is completely unaffected, while it is still the same single Julia type. And I have here some links on how you can learn more about this really, really amazing programming paradigm. So now we come to the exercise session. Wow, cool. So this is the final part. What I will do here so in general, most scientific computing disciplines have their own Julia organization and a lot of people developing and doing stuff there. So Julia might be new with respect to Python in the sense that Julia 1 was released 1.5 years ago, but this does not mean that it doesn't have a lot of stuff. It actually has a huge amount of stuff, and you should totally check them out. I list here some organizations about physics-related stuff, but many others exist as well. All right, so now what I will do is demonstrate some packages I use in my daily work, and maybe you can benefit from that, maybe not. Even if you don't have to use these packages, you could at least benefit in understanding how to use packages in some sense. Quick note, I plot in Julia using pyplot, which is the Python library for plotting, because I simply think it's the best one. And in general, you can use any Python library in Julia with exactly the same syntax, besides the indexing thingy that you have to subtract one from the indices. But you will see that I use pyplot exactly the same way as you would do it in Python. There is really no limitation. And this holds for any Python package. So let's start the tutorial, and the only thing I'm doing in this code block over here is just setting some default figure sizes. So the first package I will show is differentialequations.jl, which is by far the best differential equation solver that exists, not in Julia in general. There are some comments about performance for specific cases, obviously. And I'm not the one that claims this. This is just a comparison that has been done across all solvers. It's not me that says this. That's why I link here. This is a link that tells you, that goes to the proof. Yeah, it's not me that claims this. So, how does this work? The way you solve differential equations in Julia is very straightforward. First, you take your ordinary differential equations set and you make it a Julia function. Then you make your Julia function, you combine this Julia function with an initial condition and an initial parameter set, and you make this into an ODE problem. An ODE problem is in a specific struct that comes from this differential equations solver. Once you have this struct, you just choose the solver you want, you choose the solver options you want, and then you just solve this problem by calling the function solve. So how does this work? Let's see this in practice by solving the Lorentz system that is defined by these three equations. So the first step is to make these three equations a Julia function. And there are two ways to do this, depending on the dimensionality of your system. The first way is what is called out of place form. And you define a function. Here I call it EOM for equations of motion. And what this function does is the following. It takes the current state of your system, the parameter container P, the current time of your system T, and it returns a vector. This vector contains the derivatives of the system. So here this vector would contain x dot, y dot, and z dot. That's the first way to do this. The second way to do this is to use in place. This way does in place operations. Remember, we talked about this in the first session. And the reason to use in place operations is where you have very large arrays, like very large sets of ordinary differential equations, like 1,000 coupled ODEs or so. And the way this works is that you again define a function. Now, the first argument of this function is the container of the derivatives that is going to be updated in place. The second argument is the state. The third argument is the parameter container. The last argument is the time. All right? And typically, you want to use the first format for systems of dimension 10 or less. So this is the thing here. Here I'm using these ordinary differential equations, and I'm using the package static arrays. This provides statically typed vectors, so vectors that you cannot mutate or change their size after you have created them. These vectors are very performant when they are small. I define this function that is actually the rules of the Lorentz system, and you see here, I get the parameter container, and I have the state container and the time. I first extract the parameters, the individual parameters from the parameter container, and I extract the individual states from the state container. And then I just define the equations of motion of the Lorentz system, and then I create a static vector that has these three numbers, the derivatives, okay? This is what I have to do. The other thing I have to do is create an initial state and an initial parameter container, which is what I do here. These two lines are just the initial state and the initial parameters. And then the only thing that is left is to put everything together in an ODE problem, which is a struct for these from these solvers. Now here I have to give an additional argument that I haven't spoken about so far, which is the time span. This third argument is the time span in which I will solve my problem. So from 0 to 100 here. All right. If you want, you can choose a solver. There are, of course, default options, etc. Here I choose a 9th order solver for my problem. And then I solve this. I type solve equals solve this problem that I created here. This is the problem over here, okay? This is the problem. And I say solve the problem. And with the keyword alg, I specify the algorithm I want to solve my problem with. And the return code is success, so the solution indeed happened. So this solution object has the times of the solution and the actual vector of the solution. So these are the time points where the solution happened. And if I scroll down, these are the vectors that the solution happened. So how did this work? We didn't specify at which time points to save, but the solver we chose is an adaptive solver. This means that it solves the solution and it decides by itself what the step size should be. That's why the time points that you have here are kind of arbitrary. The solver decided what is the optimal step, time step. But how do I access the actual time steps and the actual solution? Well, it's actually simple. Sol.d, accessing the field t of the solution object, gives me the times. And accessing the field u of the solution object gives me the vectors, the solution vectors. So here I have, let me clear the cells. That's kind of, yes. All right, now it will be a bit simpler. So this gave me the third time point of this solution and the third state of this solution. You can use an alternative syntax to get these results. For example, you can access sol as if it was some kind of matrix, so to speak, with two indices. And this would give you the first variable at the third time point. Of course, you can use colon indexing as well. And for example, what I do here in this code is do a line plot of the three variables. This is what I do in principle. And it looks like this. So you see here that the time step is actually quite large to resolve the thing that happens. But because of the mechanics of this solver, you actually get free interpolation, ninth order here. This means that between any point that I have the solution, I can in fact get the solution at any time in between. What does this mean? If I type sol and call this sol as if it was a function, and give this sol the time 5.6, what the solver will do is interpolate the solution to the time point 5.6. And it will give me a ninth order accuracy of the true solution at this time point. So I take advantage of this, for example, and here I define a time vector that instead of having arbitrary dt, it has a dt of 0.01. And then I go through the solver, and I call the solver at every point in this nice equally spaced time grid. And I get the solution there. And then I plot it. And you will see that once I do it, it's of course much more smooth. There are alternative ways to do this. For example, you can use the keyword argument save at when you call the solution to save at explicit time points. But these are other options. All right. So there is this package called measurements, and what this does, it provides numeric types that have error bars, which is very useful in, for example, experimental physics. What you can do is you can solve a differential equation with numbers that have error bars, and the error bars would be propagated during the solution using linear error propagation theory. How does this happen? Well, this happens because the Julia package that solves equations, on the lowest level, it uses multiplication, addition, and subtraction to actually do the algorithm. But this measurements package defines a number type called measurement, similar with the rational number you just made in the previous exercise. And this number type naturally supports arithmetics on plus, minus, multiplication, etc. So what you could do is use this number type in your differential equation solution and get the solution with error bars. So let's see how this works. So now the measurements provides the function plus minus that creates the number 0.5 accompanied with an error bar of 0.1. And this type is, of course, of type measurement. And you see that measurement is actually a parameterized type. And I can do operations with this type. For example, I can take the square root of this number, subtract 3, and then multiply with another number that has errors. And of course, the errors will be properly propagated forwards. So what I will do now is the only thing that I will change is my initial state. My initial state was a vector of 3 numbers. The only thing that I change now is I make my initial state a vector of 3 numbers with errors. Okay, this is what I'm showing here. And in principle, you could have add errors in your parameters, but this doesn't matter. And then I create a new problem with the only difference in this new problem is that I change the initial state, nothing else. All right, and then I solve this problem. And we wait, of course. Oh, this is, I mentioned about the compilation, right? Great. So now I got the solution, and once you go down to the actual solution state, you will see that all of them have their errors. And if you are familiar with the Lorentz system, you know it's a chaotic system, so these errors should actually go to infinity at some point. And indeed they do. And then what I will do now, I don't have to explain this piece of code because you can see it earlier, but now what I will do is simply get my solution. So get the first variable. So this is the first variable of the Lorentz system with its error bars. And then I simply decompose this variable with its error bars to its actual values and its actual uncertainties, just so I can plot it, no other reason. And then I just plot this value. So what you see here is the first variable of the Lorentz system that is solved. And with red, you see how the error bars behave in time. All right? Now, why this is super duper cool? This is super duper cool because the measurements package and the differential equations package has never done anything to cooperate with each other. Never. There is no code that connects these two packages. It just works because multiple dispatch works. In principle, you could possibly do the same in Python, but you probably would have to write a glue code that would connect the two packages together. Something else that is useful in this differential equations solver library is that you can use callbacks or event handling. This means that at specific points in time, you can you can trigger an event in your equations of motion that would somehow change something. For example, let's say that you want on the 10th time point something to happen in your equations of motion, and you could do this with this event handling. So the way this event handling works is that you define some kind of condition, which is when this event will be triggered. So here I define this function condition. So once again, this is the interface that you have to see online, how you should actually define these things. I happen to know them beforehand, but in general, you have to see the documentation to know how to call them. So you first have to define a function, and this function should give you when this event should be triggered. And then you define another function that this function tells you what should happen when the event is triggered. And there are various kinds of events. There are continuous events where you check when a function crosses the value 0 and then the event triggers. Or there are discrete events where you check when a Boolean condition becomes true and then the event triggers. Here I'm using a continuous callback, which will trigger whenever the second variable of the Lorentz system crosses the value 0. Okay? This is what this means. U is the state, and 2 is the second entry. Whenever this thing becomes 0, my condition will trigger. And what my condition does is it is changing the state of the integrator to be the first entry the same, the second entry the same, but the third entry is actually decreased a bit. So when I solve this, you will see a jump of the Lorentz attractor towards the south. Doesn't make sense? It will make sense in a moment, I promise. So you use the interface of these things, and that once again you should see online for all the arguments and stuff, and then you solve again the problem, the same Lorentz problem, without errors this time, but I just use one more keyword argument to the solve function. And this keyword argument is to use this callback that I just created. So I solve the same thing again, and then I will plot it again. The code is the same, there is no difference in the code, that's why I'm running through this at the moment. We wait. So this is definitely a notebook I should have pre-run, because the time that you see here is compilation time. It's not actually running time. So this is the solution, and you see that whenever y, which is this axis, becomes 0, you see a jump towards the bottom, because the z variable becomes 0.9 of itself. All right, continuing in the spirit of extending and multiple dispatch. So Dynamical Systems is a library for nonlinear dynamics and chaos. Disclaimer, I am one of the developers. And what it does is it extends differential equations to calculate useful things for nonlinear dynamics and chaos, so to speak. And you can do this both with existing systems, so that you have known equations of motion, or you can do this with time series. So if you have known equations of motion, you simply create a dedicated structure called dynamical system, which is in fact very similar to this ODE problem. You just take your equations of motion, you make them a Julia function, the same way with the differential equations I just presented, and then you bundle them with an initial state and an initial parameter container. And that's it pretty much. So here, we are lucky because we have already defined these things before. Remember, we have defined the function Lorentz rule, that is actually the Lorentz system in the Julia function. We have defined an initial container, and we have defined some initial parameters. So in principle, I can simply use the dynamical systems library, and then I can create a continuous dynamical system by using these 3 arguments. And this is what happens here. And then I can use this object over here in many other functions. For example, if I call the function Lyapunov's, what this function will do is internally evolve the Lorentz system in time and try to estimate the Lyapunov exponents using the linearized dynamics. Whoever doesn't know what are the Lyapunov exponents, please raise your hands. Oh, wow. Okay, cool. Okay, so this is what happened here. The function evolved the Lorentz system internally and somehow created the tangent space, and then it calculated the Lyapunov
How
exponents.
do we get linearized equations?
Automatic differentiation.
No. Does one have to do anything here? No.
No, no one has to do anything. It happens automatically. So there are, of course, and there are many functions that do this. Functions that take your dynamical system and do stuff with this. For example, there is another algorithm that can calculate only the maximum Lyapunov exponent using a different method, which is what the function Lyapunov does without s. So another example is to calculate the Poincaré surface of section. For example, you have this dynamical system and you want to see whenever it crosses a specified plane, you want to record the Poincaré surface of section with this plane. And this you can do with a function Poincaré sauce, where you define here a plane. And this plane means that I want to record the Poincaré surface of section when my second variable crosses the value 0. This defines the hyperplane for me. There are other ways to do it as well. And of course, you can see the documentation for the other ways.
Indicate the direction of crossing?
You can also indicate the direction of crossing, of course. So I call this function, and this function calculates this Poincaré surface of section, which is what you see over here, this data set. And if I plot the first and the third column, I will actually see the Poincaré surface of section. The middle column is approximately 0 because this is by definition where I actually got my surface of section. So this is what I do here. I just plot the Poincaré surface of section. I don't know if you have ever seen the Poincaré surface of section of the Lorentz system. This is how it looks like. Another thing you could do is nonlinear time series analysis, which I will actually almost not touch at all. So let's say you have a trajectory of the system called the Lorentz system. The function trajectory just records the evolution of the Lorentz system at discrete time points. It is only a wrapper of this solve function I have presented so far. And I have a trajectory of this Lorentz system. What I can do with this trajectory is compute its entropy. And I will show in a moment why this is useful. So I can compute the entropy of this object over here, called the data set, by calling the function gen entropy. Gen entropy calculates the generalized entropy. How many of you do not know the generalized entropy? Okay. Do you know the Shannon entropy? It's the same thing. Okay, approximately. So you calculate some kind of entropy, and you specify how you should do this. Okay. I don't want to go into details how you should do this, because it requires you to kind of know what this thing is. But you could do it with this function. And I will skip the next part because it actually requires you to know. So now I have to go into details about the entropy. The way you calculate this entropy is you partition your state space into boxes. And the boxes have a specific size. I call here this size epsilon. And depending on the size of the boxes, the value might change. Yes. Yeah. Yeah, that is true. Yeah, I went a bit too fast because this is only worth discussing if everyone is already familiar with it. Okay, so I skip this part and I go to this nice package called distributions. So what this thing does is it provides you with an interface for writing distribution agnostic code. This means that you can write your code in a generic way without caring what is your probability distribution. And then at the end of the code, or when you run the code, you can literally plug in any distribution and it should just work. And the way this is done is in some sense similar to this person exercise. You define an abstract type. Here it's called univariate distribution. And then you define concrete types that are actually subtypes of this distribution. For example, the normal distribution or the Cauchy distribution. And this is in essence how it is done. So what I will do now is show some of these distributions, how you initialize them and how you use them. So once again, for us, the abstract type is just univariate distribution. So to create distributions, you call them for the distribution name. To find all the distributions, you have to go online to see them, okay? I'm not going to show all of them. One distribution is the normal distribution. So when I call this line, I instantiate I create an instance of the normal distribution, okay? Here, normal is a type that represents the normal distribution, and D is an instance of this type. And I could, for example, get the probability distribution function of this, probability density function of this distribution by calling the PDF function. Now, the PDF function takes the distribution as the first argument and a point in space as the second argument. But what I do here is I broadcast using this dot syntax to get the probability distribution over many different locations in space. And then I plot it. And this is the normal distribution. Of course, there are other distributions. For example, here I use the Cauchy distribution. And I do exactly the same thing. So I initialize the distribution by calling its type. And I get the distribution, the probability density function with the same syntax. Okay, but where are these things useful? These things are useful, for example, if you want to sample. So far, we have seen the rand function. The rand function gives you a random number uniformly in 0 to 1. But in fact, what this distributions package does, it is extending the Julia random function to multiple dispatch over the distribution type. So what I can now do is I can call the random function, giving the distribution as the first argument. And what this would do is it would sample a random point, but from the given distribution. So here I get a random point from the Cauchy distribution. And if I want many points, I can start to specify the dimensionality of the array I want. So this would give me a 10 by 10 matrix with random numbers from the Cauchy distribution. Something other than rand that is useful is the fit function. The fit function can take as an input any distribution and any vector of numbers and fit your distribution to this number. So try to optimize to understand what are the optimal parameters of your distribution that fit this collection of numbers. So what I do here is I create a 5,000 normally distributed random numbers. This is what this function does over here. And then I try to fit the normal distribution to these numbers. This fit returns a distribution, but this distribution has the parameters that have been optimized by some algorithm to give the best fit. I can also fit the Cauchy distribution to these numbers, these random numbers, and I get some other parameters. I can access the parameters of the Cauchy distribution that I just fitted by using the function params that just returns the parameters. Okay, that was kind of expected. And what I'm doing in this code block is just plotting the fit results, just so that you can visualize. So this is the orange is just the fitted Cauchy distribution to my random numbers. And of course, all distributions define basic statistic stuff like the quantiles, the means, the standard deviations. So I can get the quantile of the Cauchy function at 0.5, my fitted Cauchy function, or I can broadcast the quantile function, so I can get the 5% and 95% quantile using broadcasting syntax. And of course, I can call the standard deviation function for the Cauchy function. Of course, this is none because the Cauchy function, by definition, does not have does not have a standard deviation. So far, so good. Yeah? Is anyone super duper tired? But I carry on, right? Okay. All right, it's only 2 more to go, so it's okay. So the next package is the scientific project assistance software for the Julia language. Disclaimer, I'm also one of the developers of this thing. And what this thing helps you is manage your projects. And I will show you just a couple of functions so that you see how it works. But before I show this thing, I will show you something that is probably useful for everyone in the room, how you save and load files in Julia. I would assume if you want to do science, you kind of need to save and load files. So you load and save files typically using this module called file IO. This simply defines an interface for loading and saving files in Julia. And this interface works as follows. This is the interface. You use the load function to load a specific file, which you specify by a string. This string must include the path that the file is at and the file extension. And you save a file by calling the save function with the save function with first argument the file name and second argument the object that you actually want to save. All right? Now, what is important to understand is that this is only the interface. This file IO does not actually install a package that can do these things for you. You have to choose which package you want. This is an interface shared by hundreds of Julia packages that provide loading functionality depending on your extension. Let me show you what this means. Here I use the file IO and I print my working directory. This function prints where is my working directory, which is this one. And now I create some test data over here, which is just a dictionary that has 2 entries. And I want to save this data. There are many ways to save data, of course. But let's say I wanted to use the Julia package JLD2 that saves data. I cannot do this because actually I don't have this JL2 thingy installed. And I got an error. I can use another package though called bson that I have installed. And of course I use the same interface. And now this did save my data because I can just load them back. And then I remove the file so I have a clean directory. So this is how it works. It doesn't actually give you any packages to load stuff. It only provides the interface. But still, this is useful. So what we scientists typically do when we want to save some simulation is we want to store the parameter values of our simulation in the file. For example, if I was using a simulation that has the parameters A, B, and C, and I want to save the simulation, it is typical that I would use a name like simulation whatever, and then I would say A equals 1, B equals 2, C equals 3. And you could do this in Julia with string interpolation, with this $sign. So this works, but this is not extendable in the sense that I had to type one by one the parameters I have for my simulations and then equal them to their value. What is useful from this Dr. Watson thing that allows you to make this process much easier is that it provides a function that makes exactly this thing automatic for you. So you give this function called savename, where is it? Savename, a container, and this function deduces what are the keys and the values of your container and makes it into a string that maps keys to values with the equal sign. So let me make a dictionary here. Forget this command. We are not going to talk about it. So this is a dictionary. It maps the symbol A to the value 1, the symbol B to the value 2, the symbol C to the value 3. And then I can give this dictionary to the function savename, and the savename will create this string that maps keys to values. And this is useful when you want to save your data and have the parameters. And this savename function is extendable in the sense that you can have prefixes and suffixes and make all kinds of changes into this function. But in general, I won't go into the extensions more, and you can go into the documentation for the savename. Something else that would be great to have is reproducibility of your results. And you can get reproducibility using Git. Anyone that doesn't know what Git is, please raise your hand. That is excellent. So let's say that you have some dictionary that has your results of a simulation, and you save this dictionary. This Dr. Watson gives you this function tag save that does the following. It takes your dictionary that you are going to save for your result, and it adds an additional entry to this dictionary. This additional entry is the commit of the state of your repository. So the way it works is as follows. By the way, keep in mind that my current working directory is a Git directory. This works only if this is the case. So instead of writing save here, I change my save command at the end of my script to tag save. I write the name I want to save, and I give it the dictionary I want to save. Here I just use copy so that it doesn't alter anything. Optionally, I can specify where to find my Git repository. Here I say that my Git repository is my current working directory. And I save the data, and then I load the data immediately to see what happened. So the first thing I get is a warning. The Git repository is dirty. This is, of course, because I'm actually altering the stuff in my Git repository. These notebooks are part of my Git repository. My Git repository is dirty. But regardless, what you see here, I loaded the data, and you see here that I get a Git commit field in my data that has the actual Git commit. That's it. There isn't much more to it. And the rest of the data are, of course, saved as well. So that's it. This is nice. Another nice thing you can do when saving your data is ensuring you never overwrite anything, because you may have some simulation and then you attempt to save with the same name, and then boom, you overwrote your old simulation, and then many people can cry. So the way to ensure that this will not happen is to use the function save. What this function does is checks if this file exists, all right? If this file indeed exists, the function renames the existing file to the same name, but it adds an underscore number 1. And this is done recursively. So if underscore hashtag 1 exists, it makes hashtag 2, and so on and so forth. So this ensures that nothing is ever overwritten, but also nothing is ever deleted. So what I'm doing now here is I'm saving the same thing 3 more times. And remember, there is already one thing there saved. So once I do this, and then I read my working directory, so this file just reads my working directory and tells me what are the files and folders I have. This is what the readdir does. So once I read it, you will see that I have over here 4 files that have this name. This is the latest, the most recent saved file, and these are the most, it goes into the past. This is how it works. All right. What's the time? Okay. So last thing. Let's say that you have run many simulations with many different parameters, and what you want to do is collect the output and the parameters of your simulation into one large data frame. So to put it into perspective, imagine that I run some kind of simulation that has a parameter called model, it has a parameter called A, and a parameter called B. This is just my model parameters, okay? And then I perform some kind of simulation, and I save this simulation, okay? So now in my folder, I have, let's say, how many? 4 simulations that have some various different combinations of parameters, all right? I do this. This is what I do here. I just run. I just save this. There is not more to, you see, it's a lot of code, but it's not something new code. I just created this fake simulation and I just save it. That's it, nothing more. And then I create a new simulation that has some different parameters. So you will see that my first simulation had parameters model, A, and B. My other simulation has parameters model, A, and D, okay? And I save this simulation as well. Now what I want to do is I want to collect these simulations, all of them, into a tabular data format that lists me the parameters as columns, and the rows are the simulation ID, the simulation number. So, keep in mind that in every simulation I save some kind of result that comes out of this simulation and has the name R, okay? So the way you can do this is you can use the function collect results. This function takes a folder as a directory, and it scans this folder, it finds all of your simulations, and it makes them into a data frame that lists what parameters you have and what are the results of these parameters. So this is how it looks like. So these are all the simulations I have run pretty much. Now what is great about this function is that if there are simulations that do not share the same parameter, this is okay, the function still works. For example, you will see here that in this combination of parameters with the linear model, there is no parameter D, so it gets the value missing. While in the simulation with the cubic model, there is no parameter B, and it gets the value missing, but there is a parameter D. So this is how it works. And it gives you a data frame. So this is a data frame, all right? A tabular data format. This is the pandas. The pandas library has the same thing pretty much. So the last part of this session, let me delete all the data. It's just to show you how you would quickly handle tabular data in Julia. Okay. So this is a tabular data format that has all your simulations. But how do you analyze this thing? Well, to analyze this thing, you will use the data frames Julia package that allows you to do this analysis. So, for example, here I have a column that is called path, and it simply tells me where on my computer is this simulation saved. This is what the path is. But for my analysis, this is not really something useful. So what I could do is I could use this syntax over here that says, select my simulations, but don't select the column path. This is what this syntax says. So what this does is it just removes the column path from my data frame, pretty much. That is it. Something that you could do with this data frame is you could index it as if it was a matrix, so to speak. For example, if I type data frame colon 13, what this would give me is in principle just the first 3 rows of this data frame. That's it. For example, here I say results 1 to 3 and 1 to 3. So this gives me the first 3 rows and the first 3 columns. All right. This we don't have to see right now, and we go directly to the last part, which is querying a data frame. So when you have such a tabular data format, what you want to do is to somehow find parts of your data that satisfy a specific property. And you do this using the Julia package called query. Query gives you 2 types of syntaxes, but I will only show one of the 2 because I think I don't think it's simpler. I just think it has less symbols. So let's see the results. So as a reminder, this is the data frame I have, all right? And let's say I want to perform a query on this data frame. This is the query. I will first run it, and then I will explain this. So I run this query, and it gives me another data frame that satisfies my query. So how does this work? Let's see the same query, but now with comments, line by line. So this command starts a query, all right? It tells me that the from starts a query, and it tells me that my query will iterate over the rows of my results. My results is this data frame. So what I'm doing now is going row by row of this data frame, all right? Then I have this where. Where is simply a filtering expression. It tells me that only keep data from my data frame that satisfy this operation. So here what I'm doing is I'm only keeping data from my data frame whose model column is linear. Then I have a select command. This tells me which data to actually keep, to return to me as a user. As the user of the query, which data should I keep? And the last command, which is collect, simply tells me in what form should I get the returned data. And here I choose to get them in a data frame, which is the same format, because I may want to analyze them further. This is what it does. And this is pretty much the syntax of using these queries. And here is another query that is in essence the same, but it has different context. So I once again iterate over the rows of my data frame, and then I choose the rows where the cosine of my result column is less than 0.5. And then I select some new variables, because select allows you to create new variables during your query. And the select says the following: create a column that is called sine and has as values the sines of the parameter a. Create a column that is called cosine and has as values the cosines of the parameter r. All right? And collect the result as a data frame. And that's it pretty much. So my final take-home message for you, because this is at the end, I don't know if you have any mental strength to do the exercises, is the following. In my perspective, of course, this is in my perspective, but in my perspective, all the packages that I've shown you so far, all the core language and everything, has very, very, very simple API. API is simply the way you code the thing and the functions you use. It's very simple. And this is really, really important, because what is often the case is that for for students that are forced to use code bases written in very old languages like C or Fortran, there are a lot of difficulties to actually do this thing, to actually use them. But here, the syntax is so concise and intuitive that these difficulties go away. And for me, this is a very important reason to use Julia, not because it has fancy performance on it or you can use Unicode. It's because it's so darn easy to just understand what the hell is going on. So this is my final take-home message, and that's it. It's the end.